All right, so the next unit is on circular motion. The first section of this is what's called uniform circular motion. So uniform, again, is consistent, so we're looking at consistent circular motion. Now we take something that's going around in a circle, like the image on the right here. It has the same rate as it goes around in a circle, but it's made up of multiple components. Okay, the v is what's called the tangential velocity, where if you all of a sudden this thing wasn't going around in a circle anymore, you just let it go, it would go in a straight line at that given speed due to Newton's first law of motion. Okay, so that tangential velocity is always directed on a line tangent to this circle. The centripetal acceleration, centripetal means center seeking. So the acceleration is always pointed inward. Now, you might be thinking, so acceleration means change in velocity, so is it constantly changing speed number? The answer is no. Okay, the object is constantly changing direction. Okay, so the velocity is constant. Tangential velocity is constant. The radius is constant as well. So that means it's constantly changing direction. Okay, and to find what's called a centripetal acceleration, you use this formula. Centripetal acceleration is tangential speed squared, or tangential velocity squared, divided by your radius. Okay. All right, so we're going to go around this curve here. So the car is turning on a tight corner at a constant velocity, constant speed. At the top view of the motion is shown. Okay, what is the direction of the acceleration? So we have a car going around a corner. Okay, we have a center of curve, so we have a radius. All right. Now, if we look at this, so the curve of the car is following is a segment of a circle. All right, so we can say that's uniform circular motion, constant circular motion. Then the acceleration, therefore, has to be pointed towards the center of the curve. So it's accelerating in the changing direction around the center of the curve. Okay. All right. So the time interval it takes to go all the way around is called a period. So if we can figure out how many seconds or how long it takes to complete a circle, that's a period. The frequency is how often a rotation occurs, or how often a complete cycle occurs. Okay? And so frequency, period is how long it takes to make a complete rotation. Frequency is how often it takes to make a complete rotation. And they are inversely proportional. Okay? The unit for period is the second. The unit for frequency is inverse seconds, or it's also called the hertz. So if you've ever heard of like a radio frequency, they talk about 95 point something frequency on your radio. That's actually 95 point some million frequency. Okay. All right. So again, in a period, time it takes to complete one circle. All right. So we can take and we can look at our equations here. Okay, relating frequency and period, we can always rewrite this as this. So we know, okay, so frequency is 1 over the period. Okay, speed, going back to here, v squared over r. So we know that to find the speed of something, the speed is 2 pi, because that's how far you covered, times your frequency times r. R is your radius. So if you want to figure out the tangential speed of something, you can use speed is equal to 2 pi r divided by t. 2 pi times the radius divided by the time it takes to make one complete revolution gets you speed. Okay, so speed, think of it what you know. Speed or velocity is distance divided by time. Here's your distance. 2 pi r is your distance all the way around this circle, or how many times you go around. T is the time it takes to complete it. Okay, because 1 over t is frequency, we can call 2 pi times frequency times r get you your speed. Now we can put this, the speed portion of it, into the speed rearranging equation in here, and we can solve for acceleration to be, instead of v squared over r, okay, 2 pi frequency squared times r. Okay. Or 2 pi over t squared times r. Okay, there's some practice problems on this that you'll be given. You can also look up a bunch of practice problems, but if you look, the greater the radius, the greater the change, the greater the acceleration, the greater rate you change direction. Okay. So look at the frequency of a CD player. Okay, has diameter 120 millimeters, spins up to 540 revolutions per minute, or rotations per minute. Okay, when it's spinning at its maximum rate, how much time is required for 1 revolution? And if a speck of dust is on the outside edge of the disk, how fast is it moving? All right, so you got to convert 120 millimeters, which is 0.12 meters, and the radius, since the diameter is 120 millimeters, the radius is half of that, 60 millimeters, 0.06 meters. The frequency is given in rotations per minute. We need to convert that to seconds. Okay, so right now it's at 540 revolutions per minute. We know that in 1 minute there's 60 seconds. So we're going to take 540 divided by 60, get you 9 revolutions per second, or 9 hertz is your frequency. Okay, so you know your frequency, you know your radius. So because you know your frequency and you know your radius, you can say speed is 2 pi times the frequency times the radius. Okay, and that gets you your tangential speed. Okay. Now, acceleration is 2 pi times the frequency squared times r, from the previous derivation. So we put that together, you get your acceleration of 190 meters per second squared. That's the rate of change of direction of this particular spinning object. Okay. Okay, they go really fast. Okay, so another sample problem here. A hard disk rotates at 7,200 RPMs, rotations per minute. A disk has a diameter of 5.1 inches or 13 centimeters. What's the speed of a point 6 centimeters from the center axle? What's the acceleration of this disk? So the speed, okay, we know that the speed of it, the rotational speed, what's called the angular speed, is actually consistent all the way through. Okay, and if you rotate radians, so if you convert rotations per minute to radians per second, you get 750 radians per second. Think of it this way. Anything on a disk rotates at the same amount of time. It takes the same amount of time for a whole thing on a circle or on a disk to rotate, to go rotations per minute. Its linear tangential speed increases as you get farther away. Okay, so you take the radius, to find the tangential speed, you take your angular speed times your radius to get a linear speed at that point of 4,500 centimeters per second. Now, that's at the 6 centimeter point. Okay. If it goes in or out, you're gonna change your linear speed. So rotational speed is constant, linear speed changes on circular objects. All right. So let's look at a little bit more of the dynamics of this. All right. So let's figure out the force keeping something in a circle. So we talked about that the acceleration is pointed towards the center of the circle. Okay. But there's a force keeping them in the circle. And force, like Newton's second law, force is mass times acceleration. Okay, we know that centripetal acceleration is tangential velocity squared divided by r. So we can say force is mass times tangential velocity squared divided by radius towards a circle, towards the center of the circle. Okay, so we can draw the vector diagrams showing the force going into the center of the circle. So you have three vectors here. For all of them, the velocity is drawn tangential to the direction, to the circle of motion. The acceleration is pointed towards the center, as is the centripetal force. Okay. All right. So look at this. The particle of mass m is moving at a constant speed around a circle, or a constant radius, and it always has a net force of magnitude mv squared over r, pointing towards the center of the circle. Okay. Now, this is an important question. There was questions like this on the AP exam. That force is caused by a bunch of things. If it's on a string, it's caused by tension. If it's on the car on the road, that's actually caused by friction between the tires and the road. Amusement park rides, it can actually be caused by the normal force. Okay, so like if you're down here, you have your normal force pushing down or pushing you up. Because remember, the normal force acts perpendicular to the surface. Okay, so we have this. So engineers design curves on roads to be segments of circles. They also can put in dips and peaks to help with this. So at the very bottom of the dip is the normal force in the road on the car greater than, less than, or equal to the car's weight. Okay. So we have a car going with a tangential velocity in one direction. Its centripetal acceleration is going towards the center of the curve, of the dipped curve that is in there. All right. So let's look at our free body diagram here. So we have weight pushing down. We have the normal force pushing up. Okay. So the car is accelerating even though it's moving at a constant speed. All right, it's constantly changing direction. So that means when the car is at the bottom of the dip, the center of the circle path is directly above it. Okay, and its acceleration vector points straight up. So here's your free body diagram again. All right. So there's only two forces acting on this, normal and weight. And here's the thing. You got to think of which way you are accelerating. Okay? Because the acceleration is towards the center of this, there is a net force going towards the center of this. So because there's an acceleration going up, the normal force has to have a greater force. It has to be greater than the weight. Okay? Because there's an acceleration acting towards the center. That acceleration means that there's a net force acting towards the center, so a normal force has to be greater than the weight force. All right. So again, the car is turning around a corner at a constant speed, following the segment of a circle. What force provides the necessary centripetal acceleration? Okay, so it's going around a circle. If all of a sudden that force went away, the car would go in a straight line. Not a good thing around the corner. Okay. So the thing causing the turn is friction. Okay. Because if this friction wasn't applied to this, your force of friction wasn't keeping it on the tires on the road, you would go in a straight line. Okay, due to Newton's first law of motion. Because if you took away this friction force here, you would essentially have, at that point, you'd have balanced forces. And so there's no net force acting on this object, the car would go in a straight line. Okay, so you're gonna have to draw vector diagrams and free body diagrams for circular motion forces. Okay. All right, so another one here. So track and field. So track and field athlete is throwing a large hammer. Think of it basically like a big mass on the end of a string, like it says, or like on a chain. Okay. Once the mass gets moving, the athlete lets go of the chain, and it flies in a parabolic curve. The winner is the one who gets the maximum distance. Okay, so The hammer, for male hammer throwers, the mass is 7.3 kilograms at the end of a 1.2 meter chain. Okay, the world-class thrower can get a hammer up to a speed of 29 meters per second. So if that athlete swings the mass in a horizontal circle, okay, what's the tension on the chain? So really we're looking for the centripetal force being applied from the chain on the ball. Okay? So we know the 29 is the linear speed. We know we have a radius of 1.2 meters, and we know we have a mass of 7.3 kilograms. So the tension is going to be force equals mass times tangential speed squared divided by your radius. Okay? Mass, 7.3 kilograms, times your tangential speed, 29 meters per second squared, divided by your radius of 1.2 meters, gets you a tension of 5,100 newtons. That's the tension keeping that ball in the circle. When that's released, it flies. Okay, so this is what it looks like here. If we watch this, he spins it and he releases it. Okay, and it has to go at a certain speed, and it flies really far. That's almost 80 meters. Okay, 250 some feet. So that is what a hammer throw looks like. So again, when you're trying to solve the problems, we have to keep in mind that your centripetal force is going to be mass times centripetal speed squared, or tangential speed squared divided by radius. Force equals mass times tangential speed squared divided by radius. Okay. So there's a net force towards the center of the circle. Okay. So if we have this problem, we have a mass, a car with a mass of 1,500 kilograms, a radius of 20 meters. Now we're going to throw in this coefficient of friction here. Coefficient of static friction is 1. Okay. All right. So we have to figure out what's the maximum speed the car is going to make without sliding off the road. Okay. So draw your force diagram here. Okay, the force net is really the force of the friction, because your weight and your normal force are going to equal out. Okay, but so now we know the coefficient of friction. We know our normal force, which is going to be equal to the weight in this case. We can figure out our force, our static force keeping us in the circle. Okay. So we can figure out our centripetal force. Okay. Mass, the mass of the object, times the velocity squared divided by radius. We have all that information. Okay. And we know that the normal is mass times gravity. Okay. So the force static here, okay, we can rearrange, we can use the coefficient of friction equation like we did before. Okay, to solve for our Fs max. So we know, if we know Fs max is mass times velocity squared divided by r, which is also equal to that coefficient of friction times mass times gravity. To solve for V max, so we just take mv squared over r is equal to mu mg. Okay, rearrange the equation. Okay, the m's cancel, the masses cancel. So you're left with mu times g times r is equal to your speed. Okay, we know the coefficient of friction is 1. G is 9.8. And our radius is 20. Multiply them together, take the square root, you need a minimum speed of 14 meters per second to keep them in the circle. Okay, about 30 miles per hour. Okay. So this one, I'm just going to let you look through and watch and solve it. Be sure to pause this along the way so you can make sure that you know what you understand what you're doing. Okay. So one more problem. A level curve on a country road has a radius of 150 meters. What is the maximum speed at which this curve can be safely negotiated on a rainy day when the coefficient of friction between the tires and the car is 0.4? Okay. So we don't need the mass really when we're trying to find the speed. Okay. Because the force of friction is mu static times the normal force, okay, which is mass times mu times m times g. Okay, the mass cancels, okay, and just like we did in the previous question, the speed is going to be equal to the square root of the coefficient of friction times gravity times your radius to get you 24 meters per second, just like we did back here. Okay, you got to be able to put two equations together to derive the formula from it. Okay. All right, so if we're walking here, okay, at this point where your weight is sometimes greater than your net force, okay. In this case, force is down, okay. So that's the end of the first video. Make sure you look over, read the video or watch the video, read the sections, answer this formula of assessment questions, and we'll talk to you in class.